this video, we will look at one single idea, Stokes Theorem. It says you can learn what's happening inside a region by looking only at its boundary. In mathematics, the whole idea fits into a single line. The integral on the boundary equals the integral of the change inside. Let's start with something you can see. All the tiny swirls inside this floating water, they equal a single circulation along the boundary. You cannot track every little eddy inside, but look at the edge just once. The total is right there. This is not a coincidence, it is a theorem. Let's see the same idea in an everyday scene. You stir with a spoon. Inside, hundreds of tiny swirls spin, some clockwise, some counter. But look at the rim of the cup. You see the single circulation. And mathematics says the circulation you see at the rim is exactly the sum of all those tiny swirls inside. Left side, boundary, right side, interior, equal. Let's look a little closer. Take any surface, curved, flat, bent, doesn't matter. On every tiny patch, ask how much rotation is happening. This rotation is what mathematicians call the curl. Symbol is nabla cross F. Now, sum all those tiny rotations across the entire surface. Mathematics says that total equals a single loop circulation along the boundary. Every shared edge between neighbor cells cancels out. Only the outermost rim survives. That's the heart of Stokes' theorem. The interior simplifies, the boundary speaks. Stokes has a siblings, the divergence theorem. Imagine a volume. Inside there are sources, things creating or destroying something. The total of those surfaces equals the net flux going out through the surface. Left, total production inside. Right, the flow crossing the outer surface. Interior equals boundary again. A third siblings, Green's theorem. It's Stokes' theorems reflected into two dimensions. That's what Green's theorem says. But wait, where is any rotation in the expression on the right? Let's walk around a tiny square for edges, for contributions. Here is the formula. When at the map, it simplifies so that this expression is circulations per unit area. In other words, the rotation density. The difference of partial derivatives in the formula is exactly a tiny rotation. Now let's sum it across the whole region. Each little square does its own tiny rotations. Neighbored edge cancels, only the boundary is left. Same idea, just in two dimensions. Three theorems, different clothes, the same idea. Mathematicians compares all three into one single sentence. The integral on the boundary equal to integral of the change inside, no matter the dimensions, no matter the shape. Nature speaks from the boundary. We read the inside from the edge. Why is this theorem so important? Because half of physics is built on this one idea. Electromagnetism. If the magnetic flux through a surface changes, an electric field appears along its edge. Faraday's law. That's Stokes' theorem. Flight. The circulation around the wing creates the pressure difference on top. Lift. Stokes' theorem again. Thermodynamics. If a system's internal energy changes, heat or work flow must have crossed its boundary. Same idea. Each from a different field, but behind them all one sentence. Interior equal boundary.